Dear colleagues and friends, today I'm going to talk to you about transmutation of palladium induced by laser irradiation. This work has been done in collaboration with Larry Fosley and Pamela Mosier-Boss. In summary of my talk, first will be an introduction to explain why this experiment has been done. Second, we'll have an experimental setup. I will show you how the experiment was made. Then we'll see the results obtained by scanning electron microscopy. Then the analysis of the CR39, looking for neutron created by these reactions. And finally, the TOF-SIMS analysis for anomalies, isotopic anomalies. And then we'll have a conclusion. Okay, introduction. In 2016, Ubaldo Mastromatteo published a paper in which he explained a very simple experiment where he directed a laser beam on a thin film of palladium deposited on a silicon oxide substrate in hydrogen and deuterium atmospheres. By SEM, he showed formation of many new elements. He gave me two of his samples, identical samples, and recently I did the same experiment in hydrogen and deuterium. Both experiments lasted about 3 months each. The laser I used was a 5 milliwatt, 650 nanometer wavelength. This is a laser pointer, basically. You have the reference of the paper by Ubaldo Mastromatteo in the Journal of Condensed Matter Nucl Science in 2016. Experimental setup. As I was telling you, the sample is a 1 square centimeter silicon substrate with a thin chromium adhesion layer and then 350 nanometers of palladium film on top of that. The laser was a 5 milliwatt, 650 nanometers at a red pointer laser. The chamber was a quartz tube evacuated and filled with hydrogen or deuterium at a pressure of about 2 bars. The experiment lasted 3 months for hydrogen and 3 months for deuterium. Here is a schematic view of the reaction chamber. It's on a CF35 flange. There is a 30 centimeter long quartz tube, 3.5 centimeter in diameter. On top of this tube, the laser is placed perpendicular, and the sample is attached to a stainless steel rod. I will show you more on the next slide. And I can pump out the chamber and then fill it with the gas, either hydrogen or deuterium. This is a view of the sample holder on the left. You see that the sample is mounted on top of I have developed a simple system to attach the sample on the rod. On the right side, you see the laser. This is a 4 euros laser. First thing we have done is SEM and EDX analysis. It is a high quality, brand new analyzer, high resolution, with very good capacities. First, experiment in hydrogen atmosphere. We have observed different spots, but there's one which is really large. It's about 200 micrometer in diameter, hotspot. And we have analyzed on this spot 3 areas in the center, the dark black area, then 3 points in the gray area, and 3 points outside the gray area in the white area, clear area, let's say. first analysis of the three central points. So composition of point 1 shows nitrogen 44%, oxygen 68%, sodium 6%, aluminum 0.42%, silicon 0.24%, phosphorus 0.007%, sulfur 1.46%, manganese 0.14%, iron 2.94%, nickel 80%, zinc 0.53%, palladium 0.25%. Very interesting. You see, there is almost no palladium at point 1 and all kind of elements. And in particular, what's surprising is the presence of a lot of nitrogen and oxygen. Point 2 is very similar to point 1. There's a little bit more palladium. They have 7% of palladium. Point 3 also similar, and the palladium composition is also 7%. Okay, what can we say? The original palladium has almost disappeared. Some of the elements are below the 1% limit, but not all of them. Elements measured with certainty could be nitrogen, I mean a lot, 10-14%, oxygen, 52 to 68%, sodium, sulfur, manganese, iron, nickel. We have seen also low-level elements like calcium, aluminum, zinc, molybdenum. Now let's go to the next slide. Shows you the spectra. Here we have the three spectra on the same graph, showing this obviously that there is zinc, nickel, iron, manganese. The peaks are clear. Calcium. This is only the spectrum number 2. When you can see again nickel and iron, obviously there is silicon, sulfur, obviously the palladium is there. This is a blow-up area showing aluminum, silicon, phosphorus, sulfur, palladium. Now if we analyze the points in the ring, again, we have the same elements, but more palladium. You see palladium 17%, 55%, 25%, fewer elements. It's less effective than for central points, but there are still elements there. Again, nitrogen, oxygen, sodium, nickel are obviously there. Again, here a spectra showing the three spectra all together on the same figure. And now if I look at the points outside in the clear area, we have oxygen, palladium only, nothing else. It's only pure palladium and a little bit of oxygen. There's almost no, it seems that there's no reaction occurring in that area. This is a spectrum. You see the clear, there is nothing in the energy range corresponding to the contamination, to the transmutation. Same experiments have been done in deuterium atmosphere, and there we didn't see any hotspots. We did the analysis, but the analysis shows just a little bit of oxygen, 0.01%, I mean nothing, silicon 0.12%, palladium 99.78%. That means only palladium, and the silicon is probably due to the substrate. And oxygen could be to the contamination. This is the spectrum. Now, knowing that we have done, it seems that the reaction is a fission of the palladium into lighter elements. There is no elements above palladium. They are all lighter than palladium. Therefore, it was possible that neutrons have been produced because when you split large, heavy masses into smaller masses, you have extra neutrons. So we have repeated the same experiment in hydrogen with the same sample, but this time we have placed CR39 samples around under the sample, above the sample, on the sides also. I will show you the results obtained on the CR39 position under the sample. So on the same CR39, you can analyze the front side and the back side. On the front side, you can see you have counts going up to 1200, and on the back side to 150, indicating that it's not due to background emission coming from cosmic rays or something like that, since there's a large difference between the two sides. They should be about the same if it was due to some contamination due to the cosmic rays. So there's definitely neutrons being produced. Then we have done some TOF-SIMS experiments, and but in this case we have not seen so many elements as we have seen by EDX. We have looked at the isotopic anomalies of the different elements, and the ones that are showing at least 10% changes are lithium-6, 13.6% instead of 7.6 for natural, iron-54, 7.8% instead of 5.8 in natural, and copper-63, 90% instead of 69.2%. So conclusion. In the hydrogen environment, outside of the hotspot, there's no transmutation. In the core of the hotspot, in some places, palladium has almost completely disappeared, therefore excluding diffusion impurities from the sample. Elements measured with certainty: nitrogen, oxygen, sodium, sulfur, manganese, iron, nickel. Nitrogen is a gas, and nitrogen molecule is extremely stable, so it's impossible to put nitrogen by contamination. Oxygen could be due to contamination of manganese, iron, and nickel from the atmosphere, but there's not enough compared to the amount of oxide of metals there is. Sulfur, manganese, etc. cannot be due to impurities in the sample because it was pure palladium made by deposition, and there is no such elements in the quartz. In the deuterium environment, we have not detected any new element. However, Mastromatteo has detected titanium, carbon, oxygen, calcium, potassium, sodium, aluminum, and magnesium, but in less quantities, lower quantities than with hydrogen. Some experiments have been done by Lee without any laser beam. He was loading and downloading a palladium foil, and it also has shown presence of new elements. So, as a conclusion, this experiment shows new elements with hydrogen, no new element with deuterium, and we have measured neutrons under the sample and isotopic anomalies in the system also.